Okay. Okay, once again, so we will continue our training. So from 2D drawing, we will proceed to 3D drawing, and then we will show you some simulation on our drawing later on. So I will show you first what's the difference between 2D and 3D drawing. Alright, so okay. So how to create 3D drawings and simulation using CAD software. So again, we use Inventor for this training. So what is 3D drawing? 3D drawing for 3D sketching is one of the most commonly used techniques by architects, civil construction professionals, and graphic designers. It allows builders to tackle the geometric elements of height, width, and depth in their 3D projects. So these projections rely on visual perspective and aspects analysis to project a complex object for viewing capability on a simpler plane. So we just, for example, the 2D drawing just show you one side, and then if you will turn that one a little bit, so we have now 3 sides. This one, and this one. So it's 3D models now. It's 3D visual. So that's the difference between 2D and 3D. So we will just proceed to this one. So what is a 3D modeling? So 3D modeling is a technique in computer graphics for producing a 3D digital presentation of any object or surface. An engineer or designer uses special software to manipulate points in virtual space called vertices, or forms a mesh, a collection of vertices that form an object. So there's lots of, again, I'll show you again. So some of the 2D software earlier, so it's not here because they cannot use, cater 3D drawing. So again, AutoCAD is here. What else? I think just the AutoCAD left. Yes, so AutoCAD is very common. So 3D drawing or 3D software are more complex than 2D drawing. It's more heavy. The file, if you will save it, it's very heavy, but it's very, last Monday, we have a training of Tekla. It gives us more advance of how Tekla gives us a light file. It's like the trainer already draw some like bridges, or how do you call it one? Yeah, he draws some bridges, but the file is still light, like around 400 TB. That's very light. So SolidWorks, Blender is very common. 3D Max for presentation is very common as well. This one, the Rhino 3D, very common. What else? Yeah, you can experience this one in the future, in your future field, in your future career as an engineer here in Australia. You can experience some of the software. Yeah, there's lots of software in the market right now. So, yeah, that's the advantage of the 3D. You can see the whole thing, like, for example, the one that we showed to you earlier. Yeah, you can see more detail. Yeah, even without the specification, you can see, you know, you can easily recognize the model. All right. So proceed to our drawing. So if I will open again. So again, I use Inventor for this training. We'll open that again, so you can see. open that one. Yep. So now from 2D, I have now like an isometric view of our model. So if I will rotate that one, you can see from 2D the white lines. That's our grid lines. So we have now the diagonal columns, vertical columns, and also we have our beams, these yellow ones. This is our beam. So for more, so you can so that you can understand what I'm talking about. So I'll show you the video again. This one here.
It's needed to store corrosive chemicals.
And chemical storage tanks often pose a challenge just due.
See, you can see the columns there. Diagonal columns, vertical, the beams, maybe they use I-beams or wide flange. And then, yeah, the round tubular. Yeah, this one here, a small diagonal columns, just to support the whole structure on the top of the platform. So it's a huge structure.
And chemical storage tanks often pose a challenge just due to the nature of the chemicals. You're never sure exactly how it's going to react with the steel structure.
Engineers calculated that even if they lined or reinforced the tanks, they still might not last long enough. The solution? To design tanks to be fully extractable. If long-term exposure to corrosive chemicals damages them, they can simply be plucked out of the hull, sent back to shore, and replaced.
Some of these items are actually completely serial number one. They're brand new, not only to Shell, but to the world.
With all the design challenges overcome, Appomattox is now off the drawing board and into construction. In South Texas, 4 modules that form the top of the platform are being made. One provides power.
So here, we'll try to draw this one here, this platform, this assembly. So we have beams, I-beams, columns, all steel. So we'll try to draw this one later on.
Another process is oil and gas. A third is for utilities like drinking water and sewage processing. And the fourth is the living quarters. Each weighs about 10,000 tons and will be lifted onto the hull.
That lift is the culmination of 3 years of hard work and execution. And once it's set down in the hull, it's not coming back up until the platform's decommissioned 4 years later.
And now it's time to get to work on those modules and deck lifts.
I particularly like all the big lifts. And so every time we make a 1,500 ton deck lift it up and set it on 15 points without causing a flash, that's huge. That's really huge. It's really exciting to pull that off.
Enormous shipyard cranes pick up the modules, lift them 60 feet into the air, and delicately place them on the hull.
We did that 3 times. And each one was just as impressive as the last. That's why I do this.
For 6 months, construction goes non-stop from sunrise to sunset. Appomattox is transformed from a hull into an oil platform. It's now 29 stories tall, 2 football fields wide, and will house 180 personnel all year round.
I'm proud of it, and I'm proud to be a part of the team that helped push this through.
It was really amazing to be able to see something from design through fabrication and now installation and construction. We're truly driving technology and innovation forward.
The experience.
I think that's the most fulfilling, as an engineer, that you can see your design. I think that's the more very satisfaction for yourself as an engineer.
Experience was incredible. For us to be part of such an incredible project and to have the success that we actually were able to provide, it will be something that we will never forget.
In the next episode of the amazing Appomattox story, see how it tried to outrun a super typhoon on its journey across the world from South Korea to the Gulf of Mexico.
you have idea how we can build the oil rig platform from scratch, from the drawing, 2D drawing, to 3D drawing, to simulation, to construction, to fabrication. So that's why you are very important as engineers. You're very important. So you can imagine from this drawing we can build an oil rig, a huge structure. So go further. So we have the wireframe. We call it wireframe because it's all lines. So we have the beams, as what we watched earlier. We have the beams, large beams. We have the diagonal columns here. So I just make some changes because I think their platform is around 40 meters by 20 meters, but I did it 40 meters by 20 meters. So I also have, if you can see here, the dimension. It's 15 meters high. So they have 29 stories for the platform. That's very high. So I just use here 15 meters for the module. So we go further. So as you can see here, it's very different. The setting is very different with the 2D. If we go back to our 2D earlier, 2D, I just make a line. See the 2D is very I will start with see, it's very different. Our ribbons or the commands is very different to the 3D. If you go back to the 3D, it's more of like they have extrude, revolve, sweep, loft, coil. So that's the function, different functions. So if I give you some idea, for example, I make like a spare. For example, I will make maybe 20, like that, 20. Then I'll finish the sketch. Then if you go to 3D, we'll explore that one. So we have now a spare. You can see. So that's the different function of 2D and 3D. So for example, if we will revolve, so we will just revolve, then sweep. So we have some chamfer again. So for example, go back to go back here to the top. And I'll put some rectangle finish. Then I will extrude this one. For example, type 50. And then I would like to chamfer this one. Yeah, can you see the chamfer? Or you want delay. Then, for example, more value gives you more radius. Yep. For example, if you put some holes. Yep. Then you can put bolts there. So that's the basic function of the 3D. So go back to our platform. So again, we have wireframe. So I'll show you how we can go to the 3D drawings for like there's a surface in the shapes. So if I'll open the file, so we have here, so the more we go further, our file is more heavy. It's heavier, so you can see it here. So we already have, if I go to the front view, so we already have the shapes and surface of each assembly. So I have rafter like that, and floor joists. So it's more complex than the 2D. So if I come back here, if I want to put like go to sketch, I create yep, so go to our assembly, so you can see it's more of reality now. It's not already a wireframe. So go to environment, view, and change it to reality. So that's how our 3D model look like. But alright. So now we will simulate this one, so we can see how our structure will react. So I'll go to home. Again, so if you go to the new, so we have also here the drawing. So all the drawings that we created earlier, we can project it to the drawing. Like for example, if we'll open so this is our drawing. So we have the top view, we have the elevation, we have the isometric view. So if we come back here, we'll go to the base. So I can explain it to you more information how we can use the functions. So go to the base. This one here. Then we will look for our file. So which is this one here, the steel frame assembly. So open. Now we can see it's projected. This one. So this is our front view. And then if we will drag our drawing going on the top, we can have our floor plan or our top view. But it's too big for our title block for our drawing page, so we can lessen the scale. elevation, we have floor plan. You can drag that one. And then if we will double click this one, it leads us to the option. Then you can create so we have views here. Let's see the again, we go back to base, find it, find the file, yes. Then our isometric here, then we can put our side. Yeah, it's the same, it's just like the same. Okay. So now we have this drawing. So now we can put our the specification for this one. Manage. Yes, annotate. Then parts. Then find the file. Open. Yes. Okay. Then you can put the parts there. Now we have our BOM, which is tells us all the standards. As you remember, we have the isometrics, the ISO standard, which is the international standards. So all the description, steel tubes, welded and stainless. So this is our BOM for this project. So it's very simple because we did not include some of the components, like for example, I'll show you like handrails. What else? There's lots of components here. Yeah, we did not include some connections or some gauge plate or what else. Yeah, the fastener we did not include, so that's why it just give us this BOM. So imagine if you draw this one as like very detailed drawing, so it can give you a lot of specifications. Maybe a one page is not enough for this, just for the specification. And then, all right, so that's the drawing. So if we go to our like simulation, so we have, if we go to the environment, we have some stress analysis, frame analysis, dynamic simulation. So I'll go to stress analysis, and then create study. And okay. Save. Then simulate. Simulate steel frame assembly. So we have all, maybe there's some warnings. Yes, I need to put a force somewhere on the object. just try to show you how the simulation is. What happened? Maybe there's some.
I don't know why we do it.
Go
It's terrible, isn't it?
Yeah. I mean, yeah. I like to, like, she's like, why do you leave so early? Like, what's going on? And she's like, oh, you're cheating on me. And it's like,
because it's
I just like to be there.
Just wanna be
So
organized.
when we create simulation, we can simulate. So it gives us some data here, the displacement, then we can see all the reactions of each columns. Like for example, I put the force at 10,000 Newton force in the middle of the structure. So if I will animate this one,
But, like, we're just friends, and it's like, well, we've seen each other for 6 months, twice a week, every week. Like, we're going to develop a friendship. We have mutual interests as well. Like, we're both nerdy. Like, we just have common
Yeah, for
things.
the health practitioners, it's basic though, it's a boundary violation.
She's friends with like a lot of them.
Yeah.
So,
so you can see here beam details, each beam, the diagram, who, so you can give you the color of each part.
yeah, no, like,
Like, it's not ideal, because sometimes it's easy for, run a course with a client and.
So you can see here the maximum, 392.2, which is in the red. So far, our red reaction of each assembly is just the bottom of the columns. Not on the outside columns, plus on the inside columns, because our force is in the middle of the structure, because as we can see on our video,
Give me updates every 2 months.
most
like,
of the
everything's
nodes
still
are in
right.
the middle, like there's another structure in the top.
I
This
got it,
top
I
one.
got it. No.
Then you have this kind frames here, so it's more wavy in the middle structure.
she's okay with one more.
Yeah.
Like, she said the maximum is fine.
Oh, fine.
And it's not
Yeah,
really,
okay, girl.
yeah, I don't know.
Yeah.
Maybe that structure is too strong
Is that an
for,
example, though? Because I know people that
you
are
said only 10,000, 100.
Yeah,
Put it at 100.
It's just not what was, in the design of the.
I mean, mind you, like, boys are reasons, so. Yeah. Like, I know what to do with boys.
Yeah, well, I can imagine the design.
Oh, I want to too, so.
Isn't there some like things you can do now?
There's
Like,
temperatures, there's time, there's dates. Yeah. Well, apparently Katie went to go get a blood test done at Sully this week and was down
Oh, yeah.
at home. And the girl down there used to be a fertility specialist. So she's like, right, temperature has to be this. Can't do it after 13 days of the ovulation period.
And that's the problem of, like, for example,
With these circumstances.
our drawing is more complex, the file is heavy, that's why sometimes our
Tell people, like,
computer is not responding
Wow, that sounds like a lot of
Change
fun.
the load.
Alright, well, you look after yourself, and I'll see you in
I'll
like
try to
3 weeks.
put some containers.
Yeah, you too. Enjoy the sunshine.
Oh, I'll try. I'm more of a rain guy.
Yeah.
Yeah, like that. And I'll try. And we will see what happens to our structure.
Yeah. There is a
Yeah.
deflection there.
See? So, yeah, we have red one here. So it's more critical in this area. Let me try to show you how it will react. So if we go to our diagram. Go to our FX. I think my computer is not reacting. Yeah, it's because it's more heavy now, the file. So, I'll try again. We'll put another load. What's that again? 100?
Put it as 50,000. No, 100 is okay.
That's then, I'll add again. Okay, 78. So there's more load right now. Yeah, it's not really reacting, that's okay. No problem. Yeah, so it's just give us some idea how our structure react to the loads. Like you can see here, the deflection, it's more on this area because our load is on the middle. Then there's nothing happening on the sides. And also we have lots of columns on the side to support the structure. But in the middle, we only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 columns to support the load on the middle of the structure. So that's how the simulation goes. But yeah, I'm trying to animate it just to see how it bends all the steel frame, but it's not giving us reaction. That's okay. No problem. So I think that's all for our training from the 2D to 3D and then the simulation of our steel frame. So thank you everyone. Do you have any questions? Clarification, objections? Okay? thank you so much for your time and for your patience. Yes, this one. See? It's happy. So you can see here. Now you can analyze. You can make your analysis that the column, if it's too heavy, the column is not like bending. It's not bending. It's like just going away. The bottom of the column is going away like that, in this direction. And then this column is going in that direction. Then you can see how it reflects this beam here. Yeah, it's not really critical this access here, but it's more in this one because we have the continuous load. We'll try to put more loads. Now it's reacting. Stop. I'll try to put more loads, continuous loads.